In the last video, I talked about the idea of chemical bonds forming to make chemical compounds so that the system reaches a lower energy state. And now I want to take a closer look at what chemical bonds are. And if you have something like, I'm just going to draw a structure, and it doesn't really matter if you understand what it looks like or not, but like for water, for instance, I'm going to draw, and this is a taste of things to come, something that looks like that. What we're saying is there is some bond between this hydrogen and this oxygen, and some bond between this hydrogen and this oxygen that's holding them together. And if you look closer at what's going on behind the scenes, the only thing in terms of universal forces it could be, for practical purposes, is the electromagnetic force. We've got protons in the nucleus, and we've got these outermost electrons in the electron cloud, and we've got those protons in the nucleus, and then these outermost electrons in the electron cloud. And that attraction is really what holds compounds together, one way or another, some type of electromagnetic attraction. So what is a chemical bond? We're just going to put that it's an attraction between the nuclei and valence electrons, nuclei being positive, and right, those are our negative of multiple atoms, or of different atoms. And I had mentioned in the last video that I was going to try to set this up kind of in an outline fashion. I'm not going to put 1s and 2s and Roman numerals because inevitably I'll screw that up and people will get upset, but I'll just try and at least visually delineate things. When we're looking at chemical bonds, and we've mentioned these words before when we talk about like mass moles, atoms problems, and maybe nomenclature, we have covalent bonds, we have ionic bonds, we have molecules that go with covalent bonds, we had this term formula unit, and then we've got metallic bonds. So we're going to start out here with covalent bonds. If you look back at what we had said previously for the octet rule, atoms tend to gain, lose, or share. Well, one of the ways that we can reach a full octet is to share, and that's what covalent bonds do. So a key idea in this idea of covalent bonds, you've got a bond resulting from shared electrons. All right, and so highlighting what would be like the most important part to extract from that, shared electrons. If you're looking at covalent bonds, you're talking about shared electrons, and that's the key there. When we talk about a covalently bonded compound, we have a name for it that you've seen before, and that name is molecule. Right? That is a covalently bonded compound. And for practical purposes, it exists as an independent entity. This thing right here, 2 H's attached to an O, is something. We call that a molecule, all right? So I'm going to put that in parentheses. It is an independent entity, all right? Its formula says how many pieces there are, and there is something that has 2 hydrogens and 1 oxygens. And that's as opposed to ionic compounds, which go off in 3 dimensions indefinitely, and we just talk about a ratio of cations and anions. So how do we recognize if something is a molecule versus an ionic compound? We look qualitatively at the types of elements that we have. So qualitative identification and I'm going to abbreviate identification from here, ID, identification. Qualitative identification, you may recall, is generally a nonmetal and a nonmetal. So you have a nonmetal with a nonmetal. Right? And what would be some examples of that? Well, we just saw H2O, right? Or CO2, or NH3. And if you're asking, how do we know if something is a metal or a nonmetal? It's based on location on the periodic table. Everything left of our jagged line here, for the most part, we're going to treat as a metal. And everything over here, we're going to treat as a nonmetal. So as you look at this example here, hydrogen and oxygen, and I guess I'm going to hit hydrogen right there with that. So H2O Nonmetal, probably a covalent bond. They're sharing electrons. And we can look at that more closely in terms of electronegativity, which is going to be our quantitative distinguishing factor. CO2, there's carbon, there's oxygen. NH3, nitrogen and hydrogen, nonmetal. So those are all examples of covalent compounds. This is not a rule that is absolute, but it's a pretty good idea. All right, it'll give you a good place to start with that. Quantitative identification, it's nice to have some numbers. Quantitative identification can be done by getting an electronegativity difference. And electronegativity is a pretty important concept, but let's write that down first. We have some electronegativity difference. And I just want to point out that electronegativity is a big word, and I'm not going to keep writing it. I'll just write E-neg. And then, of course, for difference, diff. I think everybody will be able to interpret those things. Electronegativity difference less than 1.7. All right, so this is a line that's kind of drawn in the sand. And what I mean by that is bonds are not binary in terms of what they are. There's a spectrum. Things are more ionic or less ionic, and they rate them in terms of percent ionic character. How ionic are they, all right? And we don't need to go into that right now, but the origin of this 1.7 is that's 50% ionic, all right? So if something is less than 50% ionic, it's covalent. We're talking about sharing. If something is greater than 50% ionic, then we're talking about something that is an ionic bond. There's a give and take of electrons instead of a sharing of electrons. So just a little background information on that. Now there's actually two different types of covalent bonds, and I'll mention that real quickly. And well, it's going to have a little more importance for us when we start looking at polarity and things like that. But for right now, I just want to mention we can have polar covalent, and we can have nonpolar covalent. And those are bonds. And they actually have their own subset here of electronegativity differences. Now, we've defined polar before, but just as a quick reminder, polar, to be polar is to be uneven, right? So if we're talking in our context here, to be polar is to be uneven. All right? And if we have some polar bond, we're talking about an uneven sharing of electrons. And what determines how evenly shared those electrons are, well, it's determined by the ability of an atom to attract electrons. It's a tug of war, is what I always say. So we'll look at these here in a moment, but polar covalent bonds, as we're looking at this idea of a tug of war, polar covalent bonds have an uneven sharing. As we're talking about the sharing of electrons, all right? Uneven sharing versus a nonpolar covalent, so it's not uneven, it's even sharing. All right, and this bond resulting from whatever. You don't need me to write all those words. This is just kind of a basic idea behind that. And as I said, it's a tug of war. And if we look at something like CS2, carbon disulfide, we're looking for an electronegativity difference, and I always encourage you to use a periodic table that has electronegativity on it. And so this one that I always give out to my students has electronegativity in the bottom there. And this one, 1.9 for instance, 4.0 for fluorine, the highest electronegativity, the best, most able to attract electrons, versus down here, francium, 0.7 or whatever, the weakest at attracting electrons. And that's our tug of war. Essentially, this electronegativity is describing the strength of these atoms in a tug of war over electrons. Well, carbon has an electronegativity of 2.5. Sulfur has an electronegativity of 2.5. All right? They're both equally able to attract electrons, so they're going to have to share the electrons equally. And this is a bit of a simplification, but I think that's totally okay. So when we're doing this difference, right, I've got a 2.5 and I've got a 2.5. Doesn't matter that there's more than one. I'm just looking at the relationship between carbon and sulfur. Well, 2.5 minus 2.5 is 0. All right. So our difference is 0. And why does that matter? We're saying that it is nonpolar. They have to share equally. All right. So this has electronegativity difference less than 0.3. All right. So on this spectrum, it's basically saying anything 0.3 or lower, we're going to call equal sharing, as opposed to maybe something like H2O here. And again, it doesn't matter that we have two H's. We just need to know the nature of H, which is an electronegativity of 2.1, and the nature of oxygen, which is an electronegativity of 3.5. So hydrogen, 2.1, oxygen, 3.5. It does not matter whether I do 2.1 or 3.5. We're looking at the magnitude of the difference. So just do it big minus small. All that matters is how far apart they are. And in this case, I know I wrote it that way, but this is going to end up being 1.4, all right? And 1.4 is not 1.7 or higher, so that's got to be a covalent bond, and it is greater than 0.3, so it must be a polar covalent bond. So uneven sharing, we're talking about some electronegativity difference, and I did not space things out well, that is less than 1.7, but greater than or equal to 0.3. All right. So that did end up a little jumbled over there. So let's just say polar covalent is electronegativity difference 1.7 to 0.3. Uneven sharing, non-polar, and we've got an electronegativity difference of around lower than 0.3. And to finish out our vocabulary related to covalent bonds, I just want to talk about ways that we describe their strength and then some general properties of covalent compounds. So there is a vocabulary term that we're going to see come up, or a related term that we'll see come up for ionic compounds. In this case, we talk about bond energy. All right? And this is something that's constantly screwed up in biology textbooks especially. Let's get a definition, and I'll talk about what we have here. Bond energy is energy required. And in this case, it's energy required to break a covalent bond. All right, and that brings up some rather important information that it would behoove you to remember, and that is that breaking bonds always requires energy, all right? It's always endothermic. All right? It's always endothermic. All right? And that should make sense, because if breaking bonds was exothermic, then it would be increasing entropy, most likely it would happen spontaneously, and the bonds wouldn't form in the first place. So if you want to get two things back apart based on this idea that they went together to reach a lower energy state, then what you're going to have to do is put them back at a higher energy state by putting energy in. And I think that it's pretty easy to think of in terms of, like, if I have this pen and I want to break this pen like I'm breaking a bond, I'm going to have to apply a force over a distance. I have to do work on it to break it. That requires energy. And the reason I think that distinction is so important is that in a lot of biology textbooks, they talk about this ATP situation, and be very careful. In those books, they often say that you get energy when ATP loses those phosphates. Well, that's not true, because removing the phosphates is an endothermic process. It requires energy, right? Where the exothermic part comes in is where those phosphates then go somewhere else and form a new bond that happens to be more favorable, all right? So maybe breaking off a phosphate from ATP requires, and this is a made-up number, like 20 kilojoules of energy, but maybe when that phosphate goes somewhere else and forms a new bond, it releases, it's an exothermic process, maybe like 30 kilojoules of energy. So you have a net release of 10 kilojoules of energy with those made-up numbers. So be very, 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 very careful. I understand why biology textbooks simplify that, but boy, is that a dangerous road to go down. When we're talking about bond energy, we're talking about energy required, and I want to highlight this because we're going to see a parallel with our ionic definition for lattice energy. So when we're talking about bond energy, we're talking about energy required. Energy required to do what? To break. And what are we talking about? Covalent bonds. All right, so those are the three key terms we're going to hit on once we get to ionic compounds as well. All right, and then the last thing I want to look at for our covalent bonds are just some general properties of covalent compounds. All right, the first of these properties is that they have lower melting points in general compared to like ionic or metallic. And these are not written in stone properties, and these are not absolute properties. This is in general. So in general, we would say that they tend to have lower melting points. And just like a simple example might be water. Water is a liquid at room temperature, whereas something like iron is a solid at room temperature, right? The melting point is much lower. And that's just a simple example. In terms of conducting electricity, and this is one you may be very surprised about, but they tend to be very poor conductors. In fact, we might call them insulators. And this is something that's rather important as well. We have just established moments ago that H2O is a molecule. It has a uneven sharing of electrons, a polar bond. But if it's covalent, if it's a molecule, we said it's probably not going to conduct. And like, if you jump in the bathtub and toss your toaster in there, you're going to get electrocuted. That's not because of the water. Water, pure water, does not conduct. It's a covalent compound, and there's no way to carry charge, all right? So what is actually conducting in that bathtub water are the electrolytes, the ions from the salts that are in the water and things like that are naturally occurring, carbonates and things like that. So poor conductor insulators because they cannot carry charge. All right, and one of the things I do in lab is we get out the conductivity testers and we test the conductivity of distilled water versus the conductivity of tap water. Tap water's got all kinds of other stuff in it, and that's fine. That's what we're used to. Distilled water does not. And like, I have to have this conversation as well. All the laboratory equipment, or the distill to make our distilled water, says for laboratory use only, not for drinking. And it's not because drinking distilled water will hurt you, all right? And that's like a common misconception or whatever. It's because you don't consume things that are prepared in laboratory equipment. That's the reason. Drinking distilled water will not hurt you any more than drinking tap water will, all right? You can go to the grocery store and buy a gallon of distilled water, and you can drink as much as you want within reason, and it's not going to hurt you, right? What's the difference? A bunch of ions that are in there. Well, as soon as that distilled water touches your tongue, it mixes with spit, which is chock full of ions, and there's plenty of ions in your stomach as well. So drinking distilled water, no worse than drinking tap water. Yeah, it doesn't have any ions, but you're full of ions, so it doesn't really matter. Just, again, another side note. Water doesn't conduct electricity without other stuff, and we call that other stuff electrolytes, and those come from ionic compounds. And we'll see that terminology not too much later. All right, and the last thing I want to put is that they tend to be less brittle as solids. All right, if you think about something like a salt crystal, salt being an ionic solid, if I have a chunk of salt and I hit it, it's going to smash into tiny little pieces. Whereas if you have something like candle wax and you hit it, it may just dent or whatever. So it's less brittle, and that has to do with what's holding the particles together. In an ionic compound, you've got this interlocking lattice of ions, and in this you just have some intermolecular force drawing those closer together. And that's like one of the big overshadowing ideas of why we're going to talk about structures at all. All right, so covalent bonds, shared electrons, that's a key idea. How do we spot them qualitatively? Nonmetal and nonmetal, which we know from location on the periodic table. You've got uneven and even sharing, and also energy is always required to break a bond, and pure water doesn't conduct electricity. I think that's kind of surprising for most people.